So next, let's go through a derivation here that is also very useful and quite common situation that might arise is, let's say we have a pre-existing logic cone. For various reasons, we might have wanted to size this logic cone as small as possible to fit in a given area for layout, or potentially to minimize the amount of power going through that logic. So we have a logic cone that's already minimum size, but we need the output of this logic cone to be driving a really large load someplace. What we want to do is add some inverters between this logic cone and the large output load that we need to drive in order to and we want the minimum delay possible. So we need to figure out how many stages of inverters do we need to add in order to minimize the delay to some arbitrary output load. So how many inverters will minimize and give us the least amount of delay? So we can write our path delay, capital D, similar to how we have previously, as number of stages, capital N, times the effort, overall path effort, capital F, to the 1 over n power, and then plus our amount of parasitic delay, depending on the number of stages. So the rest of the equation is written for parasitic delay based on number of stages of inverters. In order to minimize the delay, we want to, if we take the derivative of the delay with respect to number of stages, so capital D versus dn, number of stages, that derivative, and we take that equation, set it equal to 0, and that will give us a local minimum of that curve. Now we can take that equation and rewrite it in terms of a new parameter that we're going to call rho, which we replace the capital 1 or capital F to the 1 over n power with the value of rho, and we get the equation below, which is the parasitic delay of an inverter plus rho times the quantity 1 minus the natural log of rho, and if that equals 0, if we can solve this equation, we can minimize the number of stages. So if we take the equation from our previous FOIL and try to solve it, it doesn't have any closed form solution, but if we neglect the parasitics, so we take the Pm value and equal to 0, we find that we can solve for rho a little bit more easily. Turns out it's the value of E, or 2.718 approximately. And if we are using inverters, so P sub Pm, basically the parasitic delay of an inverter, is equal to 1, and solve that numerically, we can find that the value of rho comes out to approximately 3.59. So that's for inverters, using a value of 3.59 is a very reasonable approximation of what our effort per stage should be. So theoretically, our basically our value of rho, or the effort C out versus C in, optimal in order to get the least amount of delay we determined in the last FOIL was 3.59. Question is, how paranoid do we want to get about being exactly at 3.59? So if you do a sensitivity analysis where you vary the value by different amounts from that ideal value, we can figure out how sensitive the delay is to using exactly the best number of stages or exactly the right amount of C out to C in. And so if you take if you do a graph of the delay versus the number of stages, it turns out between a value of 2.4 and 6, your delay will only change about 15% compared to the optimal value. And so it turns out, generally, I don't try to get too rigorous on being exactly at the 3.5 value. And generally, a value of 4 works out pretty well as far as it's a nice even multiple, so it's pretty easy to do. Make a gate that's 4 times the size or 1/4 the size of the previous gate. It's easy math to do, and it gets us really, really close to the optimal value. So generally, that's what I do. What basically in the book says they do, and I found that actually works out to be a really good design parameter, is using a C out to C in ratio of about a value of 4. So now that we've gone through all of that analysis on how stage delay and path delay and logical effort, and how we can use that to try and design our logic and design our sizing, let's go back to the example that we started with many foils ago. So here again, we're trying to design a decoder for a 16-word register file where each word is 32 bits wide, and each bit inside that word has a load of 3 unit-sized transistors. And so we need to decide how many stages to use, how large each gate should be, and how fast our decoder can operate. So let's go through this example and determine all of these answers. So in the initial stage of trying to come up with a solution for this example, first let's just try to get an idea of how many number of stages might be ideal in our design. Keep in mind here, we're not trying to do a dissertation and take forever. We're trying to do as quick a calculations as possible to just get a best idea of where to begin on designing this decoder. So first of all, the decode effort, it's mainly like an electrical issue. We don't have a lot of resistance and RC delay through this decoder, and we also have branching. So we have 4 selects coming in, inverted and non-inverted version. So we have our select is 4 bits, and we, like I said, have the inverted and non-inverted version coming in, and we have to drive 16 outputs that are decoded. So first, our electrical effort. Our electrical effort again is our output capacitance divided by our input capacitance for our path. We were told we had a 32-bit word that each output line needs to drive 32 bits. Each bit, if you remember from the specification, is driving 3 transistor load, so as if it was a minimum sized inverter. So we have 32 times 3 is our output capacitance. We were told our input capacitance was a value of 10. So our value for electrical path electrical effort is 9.6. For our branching effort, we need to know something about the way a decoder works. Well, it turns out for a decoder, if you have multiple bits coming in, and we have in a non-inverted and an inverted version of those bits, it turns out we only need the uninverted version of a given bit for half of our decode drivers, and we need the inverted version for the other half. So for any given word decode line that we're going to be driving, we either need for each bit in our select, we either need the inverted version or the uninverted version. So our branching effort is how many words are we driving and for a given input. So since each input is only going to half the number of words, we have 8 outputs for each input. So our branching effort is 8, and I'll kind of show that in a future foil. So now if we are trying to determine the relative number of stages, we don't know what the path effort is for the logical effort. The value of G, we don't know exactly what that is because we don't know whether we want NAND gates or NOR gates and how many inputs for each of them. So let's do our initial assumption. If we were just using inverters as the easiest example, even though we're not going to be using inverters, what would be the lowest amount of path effort? And the lowest amount of path effort would be for G equal 1. We get F equals G times B times H is 76.8. And our number of stages, if we want each stage to have, keep in mind from the previous example that we did of the ideal C out to C in, we said was approximately 4. So if we do a log base 4 of the value of F, we get 3 stages. So initially, let's start out by trying a 3-stage design, and then we can potentially modify that after we get our actual logic values in place. In the previous foil, we had determined that if we used just inverters, the ideal number of stages would be 3. However, just inverters doesn't actually get us the right logical function of a 4 to 16 decode. So we have to figure out what one possible solution. There's actually many possible solutions to get a 4 to 16 decode, but one possible solution that uses 3 stages is to take our inputs, go through an inversion first, then go through a 4-input NAND gate, and we can do a 4 to 16 decode using 16 different NAND gates that hook up their 4 inputs to different combinations of the A0, 1, 2, and 3 bits. So depending on whether for each NAND gate you either connect up to A0 or A0 bar, and then the other input connects up to A1 or A1 bar, A2 or A2 bar for the 3rd input, and A3 or A3 bar for the 4th input. So for word 0, if you connect up all 4 inputs to the non-inverted versions of the bits, you'll get the decode for word 0. For word 1, if you hook up bits 3, 2, and 1 to the non-inverted version, but input 0 to the inverted version, you get word 1. And etc. up to word 15. If all 4 inputs are connected to the inverted version, then you get the decode for word 15. So then the outputs of the NAND gates, the 16 NAND gates, will be driving individual inverters. So you'll have 16 individual inverters that then each drive their word lines. So now that we have a logical structure that we want to use, then we can go through and actually figure out what our logical effort and our path delay and gate sizes need to be. So going through that, our logical effort for this structure is taking the effort for the 2 inverters, which are a 1, multiplied together along with the effort for the 4-input NAND gate, which is an effort of 6 over 3. So that gives us an overall path logical effort of 2. Our path effort is going to be this value g times b times h that we solved in the previous slide. And so this comes out to 154, 2 times the value in the previous slide. And so we get our path, overall total path effort of 154. Now the stage effort, since we have 3 stages, we take 154, we take the cube root of that, and we get a stage effort of 5.36. So this is the minimum amount of delay per stage for this structure. Knowing this, it gives us our minimum path delay, as long as we size everything correctly, of 3 times the stage effort plus our parasitic delay per stage. So we have 2 inverters. The parasitic stage delay of the inverters is 1. Parasitic stage delay of the 4-input NAND gate is 4. And so the overall path delay comes out at 22.1. We can now use these values to determine our gate sizes, along with knowing, again, our output load that we're driving is 32 bits times 3 units of gate capacitance per bit. So that's 96. That's multiplied by the logical effort for the inverter of 1, divided by the path delay or stage effort of 5.36. And so that gives us the gate size of the inverter needs to be 18. And then we can do a similar calculation for the 4-input NAND gate driving the inverter. It has to drive 18. That gets multiplied by 2, which is the logical effort of the 4-input NAND gate. 6 over 3 is 2. And then that divided by the stage effort of 5.36. So the size of the 4-input NAND gate needs to be 6.7. So this gives us the overall path delay for this particular ideal, or the minimum path delay for this particular logical function. So this is, like I said, only one potential logical function, and we would have to replicate this calculation for various different logical functions that we think might be the minimum, and compare them to each other and decide which one we want to use. So let's look at some results of various different choices on the next foil. Below is presented a table of, not comprehensive of every possible choice you could do for a 4 to 16 decode, but at least a number of the choices that you might think would be the best choices to use for a 4 to 16 decode with this amount of C out versus C in. So below you can see one of the choices would be just using a NOR 4 gate all by itself as your decoder as a single stage. And you can see trying to use a single NOR 4 gate, because of the large amount of load that you're driving, it actually causes an extremely large amount of delay because that gate is going to be so incredibly slow. One small gate, as we said, the C in has to be only a value of 10 is what we were limited to, and that value of 10 small NOR gate would just not be large enough to quickly drive the amount of capacitive load it needs to drive. And so a single small NOR 4 gate would be way too slow and has an overall path delay of 234. Now if we get into two-stage designs, we can either do a NAND 4 followed by an inverter, or a NAND 2 followed by a NAND 4, or NAND 2 followed by a NOR 2 gate. If you go through and calculate all of the parameters for those two, they both come out approximately equal to each other, right around a value of 30. So it turns out they're fairly equivalent to each other in terms of delay, but it's not as good as the delay of the 3-stage delay that we had calculated previously. So that 3-stage delay is shown in the blue row, that we had calculated previously at a value of right around 22. And you can see it turned out pretty well, but it's not actually the minimum delay that you can get out of all the different combinations. So below there's shown more combinations that all have the same logical function. Turns out the absolute minimum delay that you can get is shown in the line in red that has a NAND 2 followed by an inverter driving another NAND 2 followed by an inverter. So basically an AND gate followed a 2-input AND gate followed by another 2-input AND gate winds up being the smallest path delay that you can get of the various different logical combinations that you can try. So this shows just how many choices you have even for a relatively simple function. In this case, you can go through, like, there's about 8 different choices here, and you could even come up with more choices than what is shown here. But the other thing to keep in mind is if you're looking at the inverter, NAND 4 inverter versus the NAND 2 inverter, NAND 2 inverter, there's only about a 10% difference in that delay. So even though, yes, there are many different choices you can choose to get the absolute minimum delay, it turns out there's a lot of choices that are close enough to each other that depending on area concerns and how many stage delays you really want in your design, and sometimes getting into your wire delays later, you might find one choice is slightly better than another for topological reasons or for wiring reasons. The number of wires that you have to route in the design and the RC delays will also come into it later, depending on just how local or how far away you need to drive your signals as well. So this page here is just showing a review of a lot of the definitions of the terms that we've used in logical effort and determining delay using the concept of logical effort. Might be useful to print this out or write down a copy of this page for future reference, and just keep it with you. It's eventually you'll kind of memorize the techniques that we've gone through here after you do it enough times, but it's good to have this as a reference. So I'd recommend printing it out, and I'm not going to go through it line by line since that's what we spent the last hour or two trying to do. So one last review of how to go through and utilize the method of logical effort. What you're going to want to do is first you compute your overall path effort, then try to estimate the best optimal number of stages that you'll need for dependent on that particular path, and then sketch out a path that has that number of stages and has the logic function that you need. And once you've got the number of stages, the logical function, and then you can go through and actually estimate what the smallest least delay is based on that number of stages and the logical function of those stages. From that, once you know what the least delay is, you can determine what the optimal stage effort is for that logic and determine the gate sizes. And basically make sure that the gate sizes work for the logic function you have, for the area that you have. And once you do that, you have at least the first pass. Here's a logic function that works and optimized for the number of stages. And you can go back and maybe look at a couple other topologies and see if the one you started with is the best one, or if there's a different topology that might be slightly better, and compare them. And once you compare maybe 3 or 4 or 5 topologies, hopefully, you don't want to do too many, because it might take a lot of time to do 24 of them, but generally the amount of effort that it takes to actually make your schematics and actually do all of your layout and go eventually through your logic and delay tool and be able to simulate the timing, doing a little bit more time up front to try and minimize the delay and create the logic that has the minimum delay is worth it in the long run. So doing this for maybe 2 or 3 or 4 up to half a dozen different logic topologies can be worth it in the long run, even if it takes you an extra half an hour up front. Hopefully it saves you days, weeks, or months later on. So that's my recommendation. It's usually a lot easier to spend a little bit more time up front and make your long-term effort be less. Finally, let's talk about some limitations of using logical effort to minimize your delay. First of all, there's a little bit of a chicken and egg problem, as you noticed like when we were going through our example. And that is that we need to know the logic of the path in order to compute our value of g, which is our overall path logical effort. But we don't know the number of stages that we actually need without knowing g. So you have to, like we did with our example, we started out just assuming g might be 1, even though we know it can't be 1, just to get an idea of the best number of stages, and then we'll pick a logical function that implements that number of stages and start with that as kind of our center point for determining what the best. So if you find out that the optimal number of stages if you were using inverters was 5, it turns out, well, you might find that 4, 5, or 6 is actually your optimal number of stages, but you won't know for sure until you wind up determining the logical function using that number of stages. So second, we're using a very simplistic delay model. We're kind of ignoring the effects of if your input coming into any given stage, depending on the rise time of that input, can actually have an effect on the delay through the logical gate. So if an input is rising really slowly, the delay through the gate is actually going to be slower than what we'll predict. There are second order effects that are being ignored by this logical effort model. Third, we're also ignoring interconnect. I mentioned that a little bit earlier. If you have longer wires, longer distance that you're traveling from where your inputs are to where your output needs to go, it's going to affect your delay more than if everything is very local and you don't really have any delay through your wires. So if you have wires with extra delay in them, you might require some iteration through your design to try and minimize that wire delay and account for it with the logic that you're implementing. And fourth, the logical effort is just trying to maximize speed. There could be implementations that you're using where you're more concerned with the area you take up or the amount of power that you use as opposed to minimizing speed. And so trying to minimize area and minimize power will give you a different answer than trying to minimize speed. So things to keep in mind, but logical effort is useful for a number of applications and will at least get you generally a pretty good starting point in trying to optimize your performance. So to summarize the overall concept of logical effort, logical effort is quite useful in thinking of delay in your circuits. You can use the numeric logical effort to characterize your gates in terms of what type of delay should be seen through them. One thing that you might note about NANDs versus NORs is NANDs are faster than NORs in CMOS because of the fact that of the way that you have, for NANDs, the NMOS are in series and they tend to be stronger devices, so increasing their size to keep the relative delay the same has less of a capacitive effect on the previous stage. So that's part of what results in NANDs being faster than NORs and CMOS. Your paths can, in general, be the fastest they can be when your effort delays are around a factor of 4. If you remember, we went through that in one of the slides. It was actually around 3.59, but averaging around 4 is a very good rule of thumb. So keep that in mind if you're, in some cases, if you're not trying to optimize an entire path or a large logic cone, but just a single delay stage, around a factor of 4 is the best rule of thumb that I usually use as well. Your path delay is sensitive to the number of stages and the sizes, but in some cases it can be kind of weakly sensitive as long as you're near the optimum number of stages and sizes. From our example that we used for our 4 to 16 decoder, when we went between a number of stage delays of 3, 4, or 5 and the different sizes and logic, we only saw about a 10% difference. So it's not highly sensitive, but it is highly sensitive when you went from like 3 down to 1. There was a factor of 10 difference in delay. So it can be much more strongly sensitive when you go down to like just one stage or when you go up to a really large number of stages. But keep in mind, using a fewer number of stages doesn't necessarily mean faster paths. In our example of the decoder, the fastest path was 4 stages. When we went down to 3 or 2 stages, we actually took longer amount of time to go through only 3 stages or 2 stages. So the number of stages isn't directly proportional to the amount of delay. Related to the NANDs being better than NORs, inverters and NANDs are usually best for driving really large caps. So that's one thing to keep in mind. And in particular NAND 2. As a general rule, if you have a really large cap that you're driving, I do not try to drive it with any 3-input or 4-input gates. And even using NOR gates, you need to size those up so large that the stages that are driving the NOR gates have to be larger or slower. So generally, inverters and NAND 2s are the best for driving very large caps. And finally, the logical effort provides a language for discussing trying to make your circuits as fast as possible, but it does require a lot of practice to really get good at. So practice, practice, practice.